Welcome to this lecture series in number theory. In this module, our goal or one of our goals is to understand the notion of an inverse of a given integer modulo n. We will satisfactorily answer the question of existence as to when exactly does an inverse exist, and on the way we will learn a lot of things. So we will continue with this project. In today's lecture, we won't be able to completely answer this existence question, but we will give a very nice partial answer to it. And most likely in the next lecture, we will answer this question fully. Okay, so let's recall a few things. Fix a natural number, fix an integer, then we define an integer b as an inverse of a modulo n if the product of a and b leaves a remainder of 1 when divided by n, or equivalently, ab minus 1 is divisible by n. So if you have an inverse, you can have many other inverses. In fact, if b is an inverse of a modulo n, then b plus n is also an inverse modulo n. And you can keep adding multiples of n and you will keep getting inverses. So there is no uniqueness in the notion of an inverse as defined here, but modulo n the inverses are unique. So if you pick any two inverses, let's say b and b prime are both inverses of a modulo n, then b minus b prime will be divisible by n. So two different inverses differ by a multiple of n, and hence modulo n they are exactly the same. So we saw all this. And then we saw a kind of a list of equivalences that you can, very important equivalences that you can associate to this statement. So if A admits an inverse modulo n, there are a bunch of other things that you can say, and I don't want to go over them line by line. You can pause the video and read it. We proved it in full detail. And if you feel uneasy about these statements as of now, the best way to learn them, the best way to let them sink in is to prove them yourself without looking at any textbook or any notes or whatever I did or anything. Just hang on, stay with them, and try to prove everything by yourself. Okay. We also developed a new language, a new perspective on modular arithmetic. Everything that you can say using modular arithmetic, you can say with our new perspective of addition and multiplication defined on z mod n z. And conversely, everything that you can say using this language, you can say using modular arithmetic. Sometimes modular arithmetic, the usual modular arithmetic, is more convenient. Sometimes this language is convenient. So let's recall some things that we defined and discussed. So first of all, what was z mod nz? Z mod nz was the set of all the remainder classes modulo n, and formally this is equal to this set, where what is this notation? If you have an integer x, then this notation is just all the integers which differ from x by a multiple of n, which we also said which we also write this way. Multiple notations for the same thing. Okay. So this is the set of all the remainder classes. This is the remainder class this is the remainder class of 0. This is the remainder class of 1. This is the remainder class of n minus 1, and so on. Clearly there are exactly n minus 1 remainder classes because the divisor, so to say, is n. Okay, so this was a set, but we defined an addition on it. So far, if this is your first course in higher mathematics, most likely you haven't seen addition discussed outside the context of usual numbers. And by usual numbers, I mean everything that is within the set of complex numbers. But in the previous lecture, we defined an addition and a multiplication on this set, which is not consisting of usual numbers. The elements of this themselves are subsets of integers. But still, we saw that there is a meaningful way to add things here. Okay. So let's recall the definition, at least for addition, and then maybe let's recall the definition for both, and I don't know how much I would like to spend time with these in the recap. So we had a map, or maybe I'll say more colloquially. So suppose I have two remainder classes, x, the remainder class of x and remainder class of y, and x and y are any integers. So then we define their addition as just add x and y and then take the remainder class. And we saw that this is well defined. There was an issue of well definedness here, because the same remainder class can be represented by various integers x. So two different people using two different representatives may potentially end up with a different answer when they add them according to this rule, but we saw that they won't, for a very, very simple reason. And in fact, this equation very neatly captures our modular arithmetic of addition, that if a is congruent to a prime and b is congruent to b prime modulo n, then a plus b is congruent to a prime plus b prime modulo n. This statement is what is here in some sense. Similarly, we defined a multiplication. We can multiply two remainder classes in the most natural way. And again, you should check that this is well defined. Okay. Fine. And then we saw that these operations, they enjoy the same nice properties that they enjoy in the context of usual numbers. So addition is associative and commutative. Associativity means you can bracket the sum in any way you like. So more precisely, it just says whether you add the first two and then add the third one, you get the same thing as whether you add the last two and then you add the first one to it. Right? So that's associativity. And commutativity means you can add in whatever order you want. So you add x, the remainder class of x with the remainder class of y, or you add it the other way around. This is a trivial statement, but has to be said. So that's commutativity. Then we have that this is the additive identity, meaning if you add it to any element of z mod nz, you get the same element of z mod nz, right? Okay, and then each element here has an additive inverse, meaning you pick an element here, you can find another element which if you add to it, you will get this guy, the additive identity, right? Just like in integers, if you pick, let's say, an integer 7, then if you add minus 7 to it, you get 0. The very same thing will happen in z mod nz also. Fine. Then we defined, or rather, then we saw that multiplication also enjoys the same properties of associativity and commutativity. We saw that this is the multiplicative identity, meaning if you pick any element of z mod nz and multiply that with this guy, you retain the same element of z mod nz. Trivial statement, but has to be said. Fine, but here is the important difference between addition and multiplication. Every element has an additive inverse, but not every element has a multiplicative inverse. The simplest example would be, just consider this guy. The 0 element, this is also called the 0 element. This does not have a multiplicative inverse. If you multiply it with anything, you're only going to get 0. That's what has been written here. So clearly, this guy does not have a multiplicative inverse. Okay. And lastly, we have the distributivity property, which says what? Which says that if you multiply to the sum of two elements in z mod nz, the multiplication distributes over the addition, just like in usual integers or complex numbers. Right, so I'm just summarizing what we learned last time. And again, I want to emphasize that we should be able to nimbly move back and forth between this more sophisticated language and the more down-to-earth language of writing congruences this way. Sometimes this language is more useful, sometimes that is more useful. Okay. Some problems for practice. And now let us get started. So the main point in this lecture is to prove a certain equipartition result. Okay, so first we will see the phenomena and then state the phenomena in general and then prove it. So what's going on? Right, so I have n as 15 and I've chosen a as 6, but I don't want to say 6. What I really want to say is the remainder class of 6. Modulo 15. But since this notation is so hefty and so ugly, it is customary and very frequent that you just write it as a usual integer and hope that the reader or the viewer is privy to the context, is tuned to the context so as to be able to understand what is meant. So here when I write 6, I mean the remainder class of 6. Okay, and all these numbers that are written on the circle are all remainder classes. So technically I should put a bracket around each of them and write a 15 at the bottom. Right? And that would make the figure extremely ugly. Alright, so what we do is we will start at any point of z mod 15z. This entire set is just z mod 15z arranged in a circle. So this is our advancer, and we pick a starting point and keep advancing, just like we did maybe 2 lectures ago. So let's say we start at 0 and then we advance by 6. So if we add 0 to 6, and again when I say 0 is added to 6, I mean the remainder class of 0 added to the remainder class of 6. We are working with z mod and z. Okay, so what happens if we do that? We get 6, right? We will land there. Then we add 6 again, we become 12. And then now we add 6 again. If we add 6 here, we get 18. What is the remainder class of 18? When I say 18, I already mean the remainder class. So 18 is same as 3, because this is same as that. Right? So we move to 3. And then we move to 9. And then we come back to 0. And then, of course, if you keep adding, you will keep cycling around. Now, suppose we choose 1 as our starting point. Then we move to 7. Then we move to 13. 4, and then 10. Then back to 1. Right? And lastly, if we start at 2, we move to 8, then 14, then 5, and then 11, finally coming back to 2. Right? But what do we observe? There is this red trajectory, I'm calling it a trajectory. There is this blue trajectory. And then there is this gray trajectory. And it is clear that these trajectories are essentially all the same, just rotated versions of each other. Right? If you just rotate the red trajectory by 1 unit, you see the blue trajectory. And further 1 unit, you see the gray trajectory. Further 1 unit, you again come back to the red trajectory. So when I say trajectory, I don't mean to record the starting point. Let's forget about where we started to develop a certain colored trajectory. If you forget about the starting point, the trajectory, starting at 3 is same as the trajectory starting at 0. Right? So this is equipartitioning the set of all the remainder classes into 3 parts. There's a red part, there's a blue part, there's a gray part. Right? So there's a very nice phenomena that we observe here. Let's experiment a little more. So this time if you advance by 10 and the same, so we are still working with Z mod 15Z. If you advance by 10, this time you will see 5 parts. If you start at 0, the trajectory is a triangle. Start at 1, the trajectory is again a triangle, and so on and so on. So this time we have an equipartition of Z mod 15Z into 5 parts. And you can play around with any A and any N and you will observe the same thing. Right? And this is what we want to now formally state and prove. Okay, so we need a few definitions before we state what I call the equipartition theorem. So fix a positive integer n and fix an element of Z mod nz. Define for each element of Z mod nz the trajectory of x with the context hidden here. So the trajectory of x is defined as this set. You have x and you then keep advancing by a. So you substitute k as 0, and when I say 0, I mean the remainder class of 0, but we just call it 0 and in fact we just write it as 0. In fact, as maybe I should have said it earlier, but as time passes, we will have the habit of writing elements here just as usual numbers. We have to develop that habit. And the context will dictate whether we are regarding that number as a usual integer or as an element of Z mod nz. And fortuitously, even if you confuse, it doesn't really make a difference most of the time. Okay. So the trajectory starting at x, or the trajectory of x, I should say, let's not call it trajectory starting at x, just the trajectory of x, is defined as this set, which is x plus, so if you substitute k is equal to 0, you get x. If you substitute k is equal to 1, you get x plus a, and so on and so on. And when I said k is equal to 1, again, I meant the remainder class of 1 because the element k is chosen from Z mod nz. So all possible elements of Z mod nz that you can obtain when you kind of start at x and keep advancing by a. That is what we saw in the example that we discussed in the previous slide. So the name for this is trajectory of x. Okay, so let's look at an example. So we have n is equal to 15 and a is 6. Again, it means the remainder class of 6. So what is the trajectory of 0? So these are all the remainder classes or the elements of Z mod 15Z. What is the trajectory of 0? So the trajectory of 0 is you start at 0, then you add 6, and then you add 6, and then you add 12 plus 16, 12 plus 6 is 18, which is 3. Right, so the trajectory of 0 is 0, 6, 12, 3 and 9, which I may write as 0, 3, 6, 9 and 12. And again, this, if I had to write in full glory, I should have written this ugly thing. This last thing is the real thing. Everything else is for notational convenience. I mean, this is a kind of a notationally dumbed down version of the actual thing. Okay, so I hope we understand what is meant by trajectory of a point. And note that the trajectory of x is same as the trajectory of a plus x. Yeah, so let's see why is that. Okay, try to prove this yourself. We will prove this in no time. Maybe in the next slide we will prove this thing. But for the moment, try to prove this yourself. And also note that the union of all the trajectories is the entire thing. So if you take the union of all the trajectories, all the possible trajectories, so when I say union, you're taking union over all elements of Z mod nz. Why is that? Just note that x lies in the trajectory of x. That's it. That immediately shows you that this union holds. So this one take as an exercise, and I really encourage you to spend time on it. It will make you understand a lot of things and make the lecture a much more smooth ride than it would be otherwise. But we will give a proof of it. So what is the equipartition theorem? The equipartition theorem says that you fix any n, then you fix any n and any a. Then for any two elements of Z mod nz, there is this dichotomy. Either their trajectories are the same or their trajectories are disjoint. There is no funny overlap business that can happen. Two different trajectories either are equal or they have nothing to do with each other. Dichotomy. Further, any two trajectories have the same size. Okay? So keeping this in mind, the fact that the trajectories exhaust the entire Z mod nz, and this dichotomy, we clearly see that the trajectories partition Z mod nz. The set of all the trajectories is a partition of Z mod nz, right? Trajectories cover Z mod nz, and two different trajectories are disjoint. That is precisely the definition of a partition. So the partition part is justified by this dichotomy as well as that remark. The equipartition, equi referring to equal, is now justified when we note that any two trajectories have the same size. So we will prove all of this. But again, try to prove it yourself. That's the best way to understand it. The easiest way to understand it. Okay. So here is a main lemma towards the proof of equipartition theorem. Fix, again, so here is the lemma. I'm making a general statement, fix a natural number and fix an a in Z mod nz. Then for any x in Z mod nz, if you pick an element in its trajectory, what you see is that the trajectory of the element you picked and the trajectory, so the trajectory of x is same as the trajectory of the element of, let me say that again. You have a natural number n, you have a in Z mod nz, you fix an x in Z mod nz and pick an element in the trajectory of it, then the trajectory of x is same as the trajectory of the element picked. That's what I wanted to say. Okay, so note that this implies what we noted in the previous page. So this implies that the trajectory of x is same as the trajectory of a plus x, right? Because clearly a plus x lies in the trajectory of x. So when we prove this, we have proven what we noted in the previous page. Fine. So let's try to prove it. So first we will show, in fact, I would say try to prove it yourself. That would be better. So first we will show that trajectory of z is contained in the trajectory of x. Okay, so why is that? So since z is in the trajectory of x, we have z is equal to x plus ka for some k in Z mod nz. Okay. Therefore, z plus la equals x plus ka plus la for all L in Z mod nz. We just added L to both sides, LA to both sides, which is equal to x plus by distributivity, right, by distributivity property and commutativity, we have this. This is true for all L, right? But this element is in the trajectory of x. After all, this is an element of z mod nz. If you add two elements of z mod nz, you're going to get an element of z mod nz. So this is in the trajectory of x. So we see this implies that z plus LA lies in the trajectory of x for all L in z mod nz, which implies the trajectory of z is contained in the trajectory of x, because these are precisely the elements in the trajectory of z. As you vary L over z mod nz, you get all the elements of the trajectory of z. So this containment has been proven. Now we will show that x is in the trajectory of z. Our assumption is that z is in the trajectory of x, but we will show the reverse. Okay, so again, I'll rewrite the previous statement that since z is in trajectory of x, there is k in z mod nz such that z is equal to x plus ka. And now here is the main point. This implies that z plus n minus k times a is equal to x plus ka plus n minus k a. And we should pause here and try to understand what is happening. What do I mean by n minus k? K was an element of z mod nz, right? So okay, so let me write this same thing in a different way so that there is less confusion. So what I will do is I will add this guy, or rather I'm adding this thing, both sides. This I will explain. So what I need to explain is what is meant by this symbol. Right, so what is this? Well, k is an element of z mod nz, so it has an additive inverse, and the additive inverse of k is denoted by minus k. So minus k is an element such that k plus minus k is equal to 0. So if k is equal to something, let's say the remainder class of some number, call it q maybe, then what is minus k? Minus k is nothing but the remainder class of minus q. And if you add the 2, you get the remainder class of 0. So it's just that every element in z mod nz has an additive inverse, which we write as minus k. So we are just adding the product of the additive inverse of k with a on both sides, which gives us that z plus minus k into a is equal to x plus, now we use distributivity. But what is this? This is the 0 element of z mod nz, because minus k by definition is the additive inverse. So this is the 0 element of z mod nz, which we just write as 0. We don't put ugly brackets. But 0 times a is 0, so I'll just erase that part. And we get that x is equal to this number, or this not number, but this element of z mod nz, which implies that x is an element of the trajectory of z. Right? So try to understand this step, what is going on here, and try to maybe write it in the language of usual congruences without using z mod nz. Try to unravel everything and see this proof in the language of congruences. That will be very instructive. Okay, so what have we done? We have shown that x lies in the trajectory of z. But by the reasoning here, this implies that the trajectory of x is contained in the trajectory of z. Right, that is what this reasoning was. If you pick an element in the trajectory of x, the trajectory of that element is contained in the trajectory of x. Here, if you pick an element in the trajectory of z, of course, the same conclusion will hold. So, if you take this conclusion along with that conclusion, together they exactly mean that the two trajectories are equal. Okay. So this is a main lemma towards the proof of the equipartition property, and I think now we can actually prove the equipartition property. Yeah, so let's just prove the equipartition property. So first we will prove the partition part, and then we will talk about the equipartition part. So let x and y in z mod n z. We want to show that either their trajectories intersect, either their trajectories are equal or they are disjoint. So either the trajectories are equal or they are disjoint. So assume the trajectories are intersecting. Assume they are not disjoint. Assume they are not disjoint. We will show that they are equal. We will show that and that will prove one part of the equipartition theorem, because what does that prove? It says that whenever two trajectories are intersecting, they are actually equal. So either the trajectories are disjoint or are equal. Okay, how do we show this? Well, very simple. Since they are intersecting, we can pick something in common. But by the previous lemma, or before that, since z is in the trajectory of x as well as in the trajectory of y, this conclusion or this clause says what? This says that actually the trajectories of z and x are equal. This is by the previous lemma. So thus, the trajectory of x is same as the trajectory of z. And since again z lies in the trajectory of y, by the previous lemma the two trajectories are equal. So we see that the trajectory of x is same as the trajectory of y, and that proves this thing. So we have proven that either two trajectories are same or they are disjoint. All that is left to prove is to show that any two trajectories have the same size. Right? So towards that, here is what we will do. So we will show that, or claim, the trajectory of x. So maybe I'll say let x be some arbitrary element of z mod n z. Then the trajectory of x has the same size as the trajectory of 0. And again, just to beat it down one more time, 0 means the remainder class of 0. Right? So we want to show this, and this will finish the proof, because it will show that all the trajectories have the same size as the trajectories of 0, and hence all the trajectories have same size. So this is the end. I mean, once we prove this claim, it will be the end of the proof. So what is the proof of this claim? Okay, let's see. Yeah, so define this map. Define a map from the trajectory of 0 to the trajectory of x. So what kind of map are we trying to define? We are just trying to establish a bijection between the two. If you establish a bijection between two sets, then the two sets have the same size. They are finite sets. If you establish a bijection, they have the same size, and there is a very natural map from here to there. What is the map? It just takes, you take k times a, map it to x plus ka. That is the map. What are the elements here? The elements there are precisely elements of this form where k is varied over z mod n z. Right? So for each k in z mod n z, just map ka to x plus ka, the shifted version of the trajectory of 0. So, okay, what I'm trying to say was, we have kind of shifted the trajectory of 0 by x. That's sort of the idea. If you remember the example that we took, the red trajectory, if you rotate it by 1 unit, it became the blue trajectory. You rotate it by 1 unit, it became the gray trajectory. That's kind of the idea behind this map. So we claim that this is a bijection. So first, this is an injection. So note that. So if f of ka is equal to f of la, then x plus ka equals x plus la. But now we have this cancellation property that we can use. We did not explicitly say anything about the cancellation property, but it's common sense. We need to get rid of this x. What do we want to do? We are trying to first show that f is an injection. To show that f is an injection, we do what? We say that, okay, suppose it has the same image on two elements. We would like to show that the two elements are actually the same. So we are trying to show that ka equals la. But this equation is same as that equation. So we're trying to get rid of this x. How do you get rid of x from both sides? You add the additive inverse of x on both sides. The additive inverse of x exists because the additive inverse of every element of z mod nz exists in z mod nz. So just add the additive inverse of x on both sides. And you get ka equals la. So therefore f is an injection. So we have just seen that this is an injection. Now we would like to show that f is a surjection, but that is clear. Clearly f is a surjection. Because any element here looks like this for some k. So you just pick that k here and form the element k, the image of that is x plus ka. So clearly f is a surjection. So f is an injection as well as a surjection, and hence f is a bijection. So this one showed that if f is an injection, clearly f is a surjection, thus f is a bijection, and we are done. All right. So that proves the equipartition property. Okay. Now let's reap some benefits out of it. So before we proceed, before we start applying the equipartition theorem to some effect, we have this very simple corollary of the equipartition theorem, which says that you fix any natural number, fix an a in z mod nz, then the trajectory of 0 divides n. Right? That's the statement. It's a very simple statement and immediate from the equipartition theorem. Because what does the equipartition theorem say? It says that the set of trajectories are pairwise disjoint and all trajectories have the same size. So you have the z mod nz, it is getting partitioned by the trajectories, but each of these parts have the same size. So if the parts, each of them have size, let's say s, then it just means that n is a multiple of s, which means in particular that the trajectory of 0 divides n. In fact, let me just change this statement and write the trajectory of x divides n for all x. It's the same statement, but looks a little better now. Right, so I hope this is clear, and now let us apply this to a certain, to obtain non-trivial results about existence of inverse. So fix a prime and fix an integer which is not divisible by p. we claim that A has an inverse modulo P, which is what I've written here. And as we have already seen, the inverses are unique modulo P, so this I will not be discussing anymore. Right, so all we are saying is that if you have a prime number and you pick an integer not divisible by P, it will admit an inverse modulo P. There will be a solution to this congruence. Clearly, if the integer were divisible by P, there was no solution to this congruence. There cannot be, because the left side would be congruent to 0 modulo P. If A were divisible by P, the left side would be congruent to 0 modulo P, and then we would have 0 congruent to 1 modulo P if there were a solution to this congruence. But since P is a prime, we cannot have 0 congruent to 1 modulo P. P is greater than 1. The only way 0 can be congruent to 1 modulo P would be that P is equal to 1, but 1 is not a prime number. So that's that. I mean, if your integer were divisible by P, there was no way that you would have an inverse. But we are saying that that is the only obstruction to the existence of an inverse. If you pick an integer not divisible by P, you will find an inverse. But this is for the prime modulus. If this were not a prime, the same kind of statement cannot be said. Try to find a counterexample to that. That will be addressed in subsequent lectures. So for now, we are happy with prime modulus. Okay, so why is this true? And let's see why. So we know that the trajectory of the trajectory of 0 divides P. So this n was actually P. Right, this is from what we just saw as a corollary to the equipartition theorem. And again, here we are already confusing between the usual world of integers and the world of Z mod PZ. Here when I write A, I mean it as an element of Z mod PZ. I have just taken the remainder class of the usual integer A and I have written it as A. I do not want to put those ugly brackets. Right, so this confusion, there is a notational confusion here, deliberate one, but it shouldn't cause any mental confusion. Okay, so we know that this divides P. So therefore, since P is a prime, we see that the size of this is either 1 or P. Because what are the positive divisors of a prime? The prime itself and the integer 1. No other positive divisors. That's by definition of a prime. Right? So if this were equal to P, then we are done. So if this is equal to P, then the trajectory of the trajectory of 0 would be all of Z mod PZ. Why is that? This is a subset of Z mod PZ. If the size of this is equal to that of Z mod PZ, namely P, then this has to be equal to Z mod PZ. So we have this equation, and hence in particular, this implies that 1 lies in the trajectory. And again, when I write 1, I mean the remainder class of 1. 1 lies in the trajectory of 0, which means 1 is equal to Ka for some K in Z mod PZ. Right? Which just immediately means that this congruence has a solution, namely K. K is a remainder class. Just pick anything in the remainder class, any solid integer in the remainder class, that will be a solution to this equation. So make sure you get it. Right? So if this were the case, then we do see that we are done. So the other case is this. So assume the adverse case is that we assume this is equal to 1. But then A would be equal to 0. Why is that? This set has size 1. There is only one element in it. 0 is already in it. and A is also there, right? The elements of this are 0, then 0 plus A, then further add A, and so on. Those are the elements of this set. The trajectory is defined that way. But since there is only one element here, these two things have to be the same. And again, I'm writing this equation as, in Z mod PZ. A is really the remainder class of A, 0 is really the remainder class of 0. But therefore, from this equation, we see that P divides A. This I have written as usual integers because there is no notion of division in Z mod PZ. So there is no confusion. This equation was written in Z mod PZ, while this is written as when A and P are regarded as usual integers. So as I said, this confusion we will constantly cause, not in order to perplex the viewer, but in order to have more effective exposition. So if this had size 1, then P divides A, but we are assuming that A is an integer which is not divisible by P. So that's contrary to the hypothesis. So that proves this very nice result, that with the prime modulus, the answer to this question of existence of inverse is very simple. The trivial obstruction is the only obstruction. Okay. Here is a stronger version of this theorem. Right, so we proved various equivalences to the existence of an inverse. And if you just look at that list of equivalences, I think the last one will prove this theorem. So what is this? Let me read it out. P is a prime, A is an integer not divisible by P, which means that A admits an inverse modulo P. Then if you scale A by all the possible remainders, so 1, 2, 3 up to P has remainder 0. So you're scaling A by all the remainders. These are pairwise mutually incongruent. So any term here is not congruent to any other term here. So this is a list of all the possible remainders modulo P, is all that I'm saying. Right? So this you should be able to see by the various equivalences that we proved. Okay. So let me summarize what we have learned. We have learned a lot of things, so I won't be able to summarize everything, but at least we can take away a very basic number theoretic fact from here. So fix a prime P and suppose A is an integer which is not divisible by P. So then we have proven by means of the equipartition theorem that A has an inverse modulo P. So we have achieved a very significant result here. And then we had various equivalences that if you have something which has an inverse modulo some integer, then we had various equivalences which I have repeated here. But the second one I want to emphasize. What is the second one saying? It is saying that if you have a non-zero integer modulo P, something that is not divisible by P, and you multiply that with A, then still it cannot become suddenly divisible by P. So you start something that is not divisible by P, and you multiply that with something that is also not divisible by P, you cannot get something divisible by P. Put another way, it says that if P divides the product of two integers, A and B, then either P divides A or P divides B or both. Both can happen, obviously. So this is just restated here. And it is such an elementary basic fact, but it is a nightmare to prove directly. Somehow it's not so easy. The way we have done it is a very long routed way to do it. There is a very simple direct proof of it, which I will probably put in the description. It's a beautiful proof by the extremal principle. Okay, what else? Yeah, so make sure you understand this point. Everything here is very important. And just restating everything here in the language of remainder classes, here we are stating it in a very down-to-earth fashion. But we have seen that everything can be recast by working in this folded world along with its addition and multiplication. So if you do that, you get this. So here you have a prime p and some element of z mod pz. When I write a not is equal to 0, it just means that a is different from the 0 element here. And what is the 0 element here? The 0 element here is the additive identity here, which is nothing but the remainder class of the integer 0. So that is what we are denoting by 0. We do not put ugly brackets and so on. We just write a non-zero. Right? And for instance, the first statement says that a has a multiplicative inverse in z mod pz. That is exactly the same statement as a possessing an inverse modulo p. Right? And this thing here takes this form now. If you product two things from z mod pz and obtain 0, then one of them has to be 0. And in the more down-to-earth language, that is written like that. And I encourage you to read all these statements and verify that indeed they are adaptations or avatars of these statements in this new language. And we need to learn this new language, so this will be a good exercise. In fact, the best would be to just recast all of this by yourself into the new language and then compare with what is written here. Okay, so I think that is it for this lecture. As usual, like, comment, share, subscribe, and I will see you next time.